Hey everyone! In this video we're going to learn how to assign oxidation numbers. So in a previous video you learned that oxidation is losing electrons and a reduction is gaining electrons. And usually, as long as we're looking at nice little ionic compounds, it's fairly easy to see what's gaining the electrons and what's losing the electrons. But oxidation numbers are a system for keeping track of where electrons are being gained and lost when it's not so easy to see, particularly in molecular compounds. So here's the set of rules that we're going to use to assign oxidation numbers, which can then be used to tell whether something's being oxidized or being reduced. Number 1. Pure elements have a value of 0. Pure elements have a value of 0. That means if you have oxygen gas, or you have hydrogen gas, or you have iron metal, or you have gold metal, all of these have an oxidation number of 0. Number 2. Monoatomic ions have a value of their charge. Monoatomic ions have a value of their charge. And some examples would be sodium plus, that's +1. Sulfur 2 minus, that's -2. Aluminum 3 plus, that's +3. So if something is a monoatomic ion, so not a polyatomic ion, we'll get to those later, it has a value of their charge. I was going to move this up because there's one extra part of number 2 that I don't want you to miss, and that's even if these monoatomic ions are part of a compound, they retain those oxidation numbers. Which means if we have something like aluminum chloride, in this aluminum chloride, the aluminum still has an oxidation number of +3. The chloride has an oxidation number of -1. Ionic compounds are pretty straightforward. That's not where the problem comes from. Oxidation numbers are going to help us later with molecular compounds. Number 3. Hydrogen is almost always 1. Anytime I begin oxidation numbers, I always say gut hydrogen. It's the first thing I check. Hydrogen is almost always +1. It's true, there are some specific examples where it's not going to be +1. So an exception would be a hydride. A hydride is when it's an ionic compound, something like lithium hydride or sodium hydride. And that's because it's not acting like a molecular compound, it's acting like an anion, where the lithium is the +1, which makes the hydrogen a -1. And in a sodium hydride, the sodium ion is the +1, and the hydrogen's acting like a -1. Otherwise, hydrogen is almost always +1. We're going to use that. Move this up, and we're going to get to rule number 4. Every time I finish asking about hydrogen, I always say gut oxygen. Oxygen is almost always -2. Again, there are a few examples where oxygen is not -2, but it's pretty much always -2. An example of an exception would be if rule 3 messed it up in hydrogen peroxide. In hydrogen peroxide, it's not -2 because the hydrogen is +1 and it forces the oxygen to be something else. In this case, the oxygen is a -1 to keep this neutral. But otherwise than that, oxygen is almost always -2. Number 5. What happens if it doesn't contain hydrogen or oxygen? So I always start off with got hydrogen, got oxygen. So if we have something like carbon tetrachloride, we would have checked to see if we had an oxygen. We checked to see if we have a hydrogen. We got neither one. The most electronegative element gets its preferred charge. If you're not sure which one's the most electronegative, it's typically the element that's further to the right and up on the periodic table. Think your halogens, definitely not the carbon. In this case, chlorine is the most electronegative. Chlorine's preferred charge, I went to go say it earlier and I messed it up. Chlorine's preferred charge has become chloride, which is a -1. So we get that -1, and that's how we can assign something. Another example of that would be if we had SF6. If we have sulfur hexafluoride, we check to see if we have a hydrogen. We do not. We check to see if we have an oxygen. We do not. Which one is going to get assigned an oxidation number first? It's going to be the most electronegative. In this case, the fluorine. Fluorine's preferred charge, if it forms an ion, is the fluoride -1. Now, actually, this helps us out because rule number 6 is the sum of all oxidation numbers in a molecular compound must be 0. So, when we had carbon tetrachloride, if this chlorine is -1, and there are 4 of them, we need this carbon to cancel out these 4 -1s. What that means is that this carbon, in order to cause this to have a sum of 0, must have an oxidation number of +4. That's the only way that the sum of all oxidation numbers can be 0. In our second example, the sulfur hexafluoride, where the fluorine has -1 and there are 6 of them, the only way that this can cancel out and become neutral at 0 is if this sulfur has an oxidation number of +6. One last rule. Our final rule, rule number 7, the sum of all oxidation numbers in a polyatomic ion, the sum of all oxidation numbers in a polyatomic ion must equal the charge of that polyatomic ion. Ooh, so it's just like the molecular compounds, except instead of adding up to be neutral, it has to add up to be the charge of the polyatomic ion. An example, sulfate. In this sulfate polyatomic ion, I would first check to see if I have a hydrogen. I do not. I would then check to see if I have an oxygen. Oh, we do have an oxygen. Oxygen is assigned the number -2. In this case, we now have to make it so that the sulfur has a value to combine with the 4 oxygens so that it equals -2. There's actually a little bit of algebra here, because with 4 -2s, it's -8. I know that the sum of whatever this sulfur is going to be plus the -8 has to equal -2. The only number that this S could be, so that it combines with the -8 to become -2, would be +6. 6 plus -8 equals -2, which means the oxidation number of this sulfur is +6. And this was a rundown of the rules for assigning oxidation numbers.